At T0, the storm's energy physically collides with the Earth's magnetic field, violently warping the protective shield around the planet. In the upper atmosphere, the sheer force of the energy strips molecules of their electrons. This sudden influx of free electrons instantly kills high-frequency radio communications across the sunlit side of the Earth.
Further up in orbit, the distorted atmosphere blocks GPS signals, cutting off vital navigation systems. Losing GPS disables precise timing applications that synchronize the global supply chain and international financial transactions. Before a single terrestrial power line feels the impact, the invisible digital synchronization holding modern society together completely evaporates. At 2 hours past impact, the full force of the geomagnetically induced currents pushes through the soil and bedrock to the surface. The grid's primary bottleneck is here: extra high voltage, or EHV, transformers. These heavy-duty components are forced to absorb the massive influx of DC energy. We know exactly what this looks like. During a smaller solar storm in March 1989, a transformer at the Salem nuclear plant in New Jersey was critically damaged by a GIC overload. The DC current overloads the system so severely that the copper windings inside the EHV transformers literally melt from the inside out. If a Carrington-scale storm hits the U.S. eastern seaboard and Midwest, these transformer failures will instantly cut power to between 20 and 40 million people. This is a physical burnout of the grid's most vital organs. A blackout caused by melted hardware cannot simply be rebooted. At T+24 hours, local terrestrial backup generators run out of fuel, and the crisis extends to the ocean floor, where long-haul cables carrying global internet traffic reside. These submarine cables stretch across continents, relying on electronic repeaters spaced every 50 to 150 kilometers to boost the data signals along the route. The extreme magnetic fields generated by the solar storm easily compromise these deep-sea repeaters, shorting out the electronic components that keep the data flowing. Once those cables fail, isolated regional power outages become a global communications collapse, digitally severing the continents from one another.